Yeah, thank you. Thank you for this opportunity for making presentation from Japan. And I'm very sorry that I could not physically present, but I would like to make this presentation or interaction as lively as possible. So today, in this IoT session, I'm going to talk about the directory service system that we have developed in last few years. And this directory system is used for for the management of IoT devices as well as management of the IoT data. Outline is like this: background, then related work, and then the components, some sort of implementation overview, use cases in Nepal, and finally conclusion. So as we know, this may be, I can skip this because this is IoT session. So IoT is key component for next generation of ICT. Many new networks like 5G and beyond 5G networks will connect billions of IoT devices for massive machine type communication services. And when we have billions of devices, we need scalable low latency directory service. So directory service is used to store just a moment, profile of billions of IoT devices, and also to store the IoT data generated by the devices. So we have two types of data. One type is the data about the IoT devices, maybe the location of the IoT device, or maybe the what we call some security keys or certificates, or the addresses of the IoT devices. And other data is the data generated by the IoT device. It may be data coming from the sensors like temperature, pressure, or rainfall, or whatever we are measuring. That would be the IoT data. And in today's presentation, my focus is to store profile of billions of IoT devices. In our research, what we have done, we have assumed that each IoT device would have a number of records, and in each record we have attributes and values. For example, if the attribute is location, then the location also we may have the type, like if it is a GPS location, or if it is the geographical location, or if it is like some sort of address, like IP address type of location. So we can have different attributes, different types, and different values for the record. And it is also based on ITUT X.501 standard. And regarding the time, like when we want to have some secure communication between IoT devices, let's say for automation and driving automation, then what happens if you want to know whether the message you have received from your neighboring car is authentic or not? You have to know the certificate or credential of the neighboring car or the message sending car. Then what happens? You just inquire or make a query to the directory service. You get instantly the response, and then based on the response message content, you can decide whether the message is genuine or not. So such type of if we are considering using IoT directory service for such mission critical applications, then we came to know that the IoT device lookup profile lookup time would be about 10 milliseconds. So within 10 milliseconds, we must be able to get information about IoT devices. And for that type of time critical applications, we cannot use existing directory services like the popular is DNS. DNS is good for static information, but if we want to store some dynamically changing information and perform low latency or latency guaranteed lookup, it's not supporting. There are number of research activities in the past, like Auspice, MDHT, Kodo, NS, and also a series of recommendations developed in ITUT X.50 series. There are such directory service systems, but they have all limitations as listed here. And to address those limitations, what we have proposed IoT directory service system like this. So in this case, what happens? The IoT devices first store their information or profile records to a private directory service system. And in this private directory system, we have some sort of filtering mechanism which filters private information, and the public information can be stored in authorized public directory service system. And from the authorized public directory system, the other directories service clients, we call them cache servers in our generic language. So those cache servers, they can download the records from the public directory service, and they can store the records near by the clients. So this is one example of automated driving. So let's say one car whose private network is somewhere here, moved to another location here, and if it is sending some message to the yellow car, then what happens? The yellow car has to get information about the red car. And in order to get the information about the red car, it will be asking the directory service cache servers, and this directory service cache server contains information about the red car. This type of caching will follow the location of the car, because this car has moved to this network. It means this directory service would fetch the data related with this car in advance, so that any car, like yellow car, when requesting for data about this car, that data, that record would be available instantly. So this type of prefetching of the records based on the location of the IoT devices is being proposed and implemented. And these directory services, the client side directory services, can be implemented in edge computing platform by leasing resources from the cloud service providers or edge service providers. And here I have listed a number of features of this directory service. It performs on-demand caching of the records. As I mentioned earlier, it is following the location of the IoT devices. And it also performs tracking of the caching points, because those points need to be updated when there is a changes in the record. So we also need to continuously track where the records are stored. Then also the records having various attributes, as I mentioned earlier. In case of the vehicle, it may contain vehicle ID, owner name, location, direction, security keys, certificates, etc. And then information stored in the directory service can be looked up with the heterogeneous keys. So we can either search by ID, or search by name, or search by location. And as I mentioned earlier, we target to make the performance guarantee in terms of the lookup latency by dynamic resource provisioning to the edge devices. This is another example when using in the automated driving. So what happens? Let's say this car has got this car has sent some message to the red car. The yellow car has sent some message to the red car. Then what happens? The red car doesn't know about the yellow car, so it doesn't know whether the message is genuine or not, whether the message is coming from some authorized vehicle or not. Then what happens? It sends a lookup message to the nearby directory service cache servers, and it obtains response. And the response can be obtained through different channels. One may be it receives a response directly from the directory service, and directory service is attached to the roadside unit RSU. And another, maybe it can obtain the record from the cellular network base station. So different path or multi-hop connection multi-hop or multi path connection can be used for obtaining the record for the safety purpose. So by using this type of directory service, what we can do, we can avoid like collision in the intersections, because they know each other and they know that the message coming from the neighboring car is genuine, and they take precaution in advance and avoid the collision. So this is one example. And we also have thought of implementing this type of directory service in the cellular network system. So what we have proposed here is the directory service system can be, the central directory service system can be somewhere in the cloud service, and the edge or the cache servers can be located into the edge. So this is one example, and this edge system is directly connected to these roadside units as shown here, so that we can reduce the latency. We have implemented this system in Linux, and as this is related with the small devices, we have also implemented it in Raspberry Pi devices. And data for the database or the resource management, we have used Docker containers and MongoDB. We have used MongoDB because MongoDB allows us to store non-structural data. So that's why we have used MongoDB, and the components are shown here. As you are already familiar with the virtualization system, we have the virtual platform of Docker container. What it does, it virtualizes CPU, memory, storage, bandwidth, resources, and each container's resource can be dynamically adjusted. We allocate some resource to the container, but if we have a lot of workload, then what happens, its performance might not be meeting the requirements. Then what we have to do, we have to dynamically add virtual CPU, memory, or storage, whatever needed, so that performance will remain intact. And then in the lookup process, we also have adopted some sort of like the priority caching or then scheduling mechanism, so that the lookup latency would always be guaranteed. There would be no head of line blocking or any like deadlock in the lookup process. And then these devices are continuously monitored through the resource controller module. It monitors the resource usage and performs adjustment immediately. Yeah, this shows an example of the record. So in record, we have ID, object ID, then this is some sort of ID. And then the record information is stored in JSON. We called it dictionary. So a JSON format, you are already familiar. It contains tag and the values like this. It shows how IP addresses or some sort of binary keys are stored in the directory service. And we did some experiment as on here. What are here are that we have the directory server, central directory server. Then we have some sort of network here, core network, access network, and then we have the edge cloud type of device for the replica or cache server. And then what we have done, we have assumed this as a IoT gateway, and these are the IoT devices. For the experiment, we have just used the virtual machines as IoT devices, and we verified that when we increase the number of client, and each client sending lots of requests per second. Like let's say in our experiment, we had maximum 10 clients, and each client can send at most 100 requests per second. And the network latency is assumed to be 0.3 to 5 millisecond, and number of records to be looked up are 100K or 100 million. So in this type of environment, we did the evaluation and we found that the lookup latency in case of the 100 record would be about 5.56 millisecond. And in case, even though we have 1,000 records, 100 million records, then again the latency is almost the same. So in this case, we have verified that our architecture provides guaranteed lookup latency. And in case the network latency is very high, let's say it's if we are using some slow network, then in this case, of course, depending upon the network latency, the lookup latency will be additionally high. For example, if the network latency itself is 5 milliseconds, then of course we need 5 milliseconds for the lookup, and the total latency would be about 10 milliseconds. So what we have measured local update latency and the global update latency. The previous was about lookup latency, and now we are considering the latency required to update the record, because we are considering dynamic IoT devices whose record may change at any time. And we did this experiment and we found that the this update is also quite fast. It's about 2.9 millisecond. And if we have many replica servers, many cache points, then what we have to do, we have to update them all. So it would be taking a little bit high, about 60 millisecond in average 50 milliseconds. We are also exploring the possibility of deploying IoT direct services in various services in Nepal. We discussed with like our colleagues in ICT 4D about the possibility in transportation area, in pollution monitoring area, or the patient caring in hospitals, and of course trekking, climbing route monitoring in Himalayas. And some examples are shown here. It's about the pollution monitoring in cities. We have the devices connected to local access points, and those access points can be NobNet access points, as presented previously by my colleague Dr. Owada. And in tracking route also, let's say IoT devices are being carried by the trackers, and there are access points on the way. Then the trackers health condition or trackers location, whatever sensors they have would be regularly monitored from the distant servers. So this is the end of my presentation. I presented the design of an IoT directory service system, which is capable to store records of huge number of IoT devices, and we have been considering millions of devices, and targeting the lookup latency of about 10 milliseconds for supporting critical applications like driving automation or the emergency rescue systems. And we have implemented it in Docker platform with no SQL data like MongoDB, and making the interfaces independent of database architecture. And we also have evaluated the performances. Raspberry Pi version is also available. So in case you are interested in using Raspberry Pi version of the IoT directory service, we can give you the software by establishing very light MOU with our organization. Thank you very much.
Thank you very much, Professor. And is there any question, comments for this presentation? And also the virtual participants, if you have any comments, ask questions. Oh, okay.
Okay, thank you for a good presentation. I like it. I want to collaborate with you or your organization for the patient care IoT. How can we reach you? Thank you.
Thank you very much.
Yeah, thank you for your interest in our research and this IoT directed service system. Yeah, if you want to collaborate with us, what you have to do, you have to first write down the use case scenario where you have been considering to apply this directed service system. Maybe in order to write the use case scenario, you must know the capabilities and limitation of the directed service system. So you can read our papers published online. We have several papers published in IEEE, like Communication Magazine, also in some conferences and other journals. In case you could not get those papers online, then you can directly contact me. My, let me check whether I have mentioned or not. My contact email address, not available here, but I'll be glad to give you my address. You can also consult with the chair, my colleague Owada-san, who is physically present there. He will be providing you more detailed information about our contact. And once you find that this directed service is really applicable in your target use case scenario, we will be very happy to collaborate. We will establish some sort of MOU and we'll give you this technology free of cost if you are belonging to research organization or NPO organizations. Thank you.
Sorry, I haven't given my introduction. I am Pramod Gamali and I am from the medical university. That's we say in Patan Academy of Health Sciences, and we care. We teach the medical students as well as we care the people of Nepal. Thank you. Tertiary Care Hospital.
Yeah, thank you, sir, for introducing yourself. And then there would be no problem in collaborating with you because you are an academic institute and we are a government research institute. So we look forward to further correspondence with you. Thank you.
Thank you very much. So I will provide his email address and also Fuba, his contact point. You can find the on the Fuba applications. So thank you very much, Kafre-san. And is there any question and comments for him? Okay, so time is a little bit over. So thank you very much, Kafre-san.
Thank you so much.
And this first session is closed here. And the next session will start around 11 a.m. here. So let's take a break. Thank you. Okay. No, I can. Yes.
Hi, Amano.
Good morning. Hi, Sebastian.
Hello.
Can you hear me?
I can. Can you hear me?
Yes, yes. I'm sorry I couldn't make it because I had other things on this week before coming. I couldn't come to Kathmandu. Have you done any hiking?
No, it's all a bit unlucky for me. I'm physically in Kathmandu, but I'm joining from my hotel room because it seems like I finally got COVID.
No kidding.
No kidding. I left the conference on Tuesday just feeling like I had a cold, and I was it really feels like a normal cold. But in order to be sure, I did a quick test and it showed positive, and then we did a PCR and it confirmed. So I don't feel very bad, but I don't want to go to the conference and put others at risk, maybe. So
Of course, yeah.
but yeah, it basically I'm confined to my room. I'm at hotel the whole day and just waiting, basically.
Too bad.
So no trekking, no climbing, nothing, unfortunately.
Well, maybe next time.
Yeah. So
Yeah, nice to meet you. This is Yasunori Owada, the chair of IoT working group. And thank you very much for your participation. And the sequence of the presentation is one, first, how do you pronounce your name? Pietro Semimori? It's okay?
Whatever, that's fine.
Okay. You will present first, and next is Sebastian. And the last, the Navi Ashur. Okay, okay. Mhm. So this
yeah,
sequence.
it's good that Amano is starting, because then I assume you will be introducing some of the technologies, the protocols, the standards, and it makes a lot of sense if that comes first.
Okay, so please wait 15 minutes.
Amano, are you still there?
Yes,
Can you
but
see my
I was
screen
supposed to
right
be
now?
the first one.
What's that?
Which is the order of the presentations?
I think you are starting.
Okay, because I see your presentation.
Yeah, I
On the
think it was
screen.
changed. I think it would be good if you started so that the technologies get introduced, because I will assume that people know a little bit about LoRa, and it would make more sense if yours came first. But personally, I
Indeed.
don't.
Indeed, it does make sense. No, I was just confused because I saw that the screen is showing your
Yeah,
presentation.
I think it changed it a little bit. Are you currently seeing my screen, Amano?
Yes, I'm looking at your nice satellite screen.
Yeah. Good. Okay, that works. I was just confirming that that was okay. Nice.
Hey, Epano.
Hi. Good
How are you?
morning.
Good morning. Oh, sorry.
Hermano,
Yes,
I can hear me, right?
you're welcome.
Okay, all right.
Okay.
Should I send my presentation just in case?
Did you say something, hermano? Can you repeat?
I say, would you like me to send my presentation just in case?
Yes, please.
Whom should I send it to?
I think you can send it to me. That's fine.
Okay, can you put in the chat your address?
Maybe you. Okay. Okay, give me a second, okay?
Sure.
Oops. Hermano?
Yes.
Yeah, so you got my email, right? I just I just texted on the meeting chat. Did you see it?
Yes, now I see it. Thank you.
No?
Yes, and now I see it. Okay.
Oh, okay.
It was hidden, but now I can see it. I will send you the presentation.
I think that should be fine, but it just in case.
Yes. Okay. I just sent it to you.
Okay, hermano, I just received it. Okay, thank you.
Great.
Okay, it's almost a time to start next sessions. And the next session of IoT working group, there are three presenters. The first one is Pietro Emily Hermano, and he will present LoRa IoT communication systems. So if you are ready, please start. Oh, this is, yes. Sebastian, could you turn off the screen sharing?
I am not screen sharing. This
Oh,
is
really?
Sebastian here.
This is a Sebastian's screen.
What you are seeing now must be Amano's screen. It's not mine.
Okay, okay. So Emmanuel, can you hear me? The Emmanuel, the mic is muting. Oh.
Can you hear me now?
Yes, but the voice is a little bit small, I think.
Okay. I'll try to speak louder. Can you hear me now?
Yes. But I did.
Maybe your microphone is far.
Yes, please. Okay.
Yeah, okay.
So if you're ready, please start your presentation.
Okay. My name is Hermano Pietrosemoli. I work at the International Center for Theoretical Physics in Trieste, Italy. And I've been working in a lot of projects with my friend Sebastian, which is also presented today. And I'm really would like to have been there in person, but I will still try to address some questions from the audience. Today, I will deal with connectivity issues related with the Internet of Things. Can you hear me now?
So sorry, your voices are very small. So if you can change some microphone settings.
Okay. Okay.
Yeah, get better.
Okay, good. Sorry, it was a problem with my headphones. Okay, so we'll talk. If you can hear me now, we'll go again to the.
Yes, please go again.
Okay. Okay, so the connectivity issues related with IoT are mainly that we need to have low power consumption in order for the battery to last several years. Otherwise, replacing battery is very cumbersome and costly. And we need to have small size and, of course, low cost because we want to deploy many, many devices, and it would be possible if they were expensive. And we would like, particularly in many applications, to have long range and deep penetration capabilities. This is not always required, but in many cases, it is very useful. especially, for instance, if you want to have a meter in the basement of a building, then you need to have a high power budget in order to be able to traverse the floors and the walls of the building and still get a reasonable signal. So these requirements are not really met by Wi-Fi and legacy cellular technologies because they were designed for short range and high bandwidth, which is not normally the case of the requirement for IoT. So in general, the IoT connection is that you have some sort of sensor or actuator or a node, and it connects by wireless to a gateway or a base station. And from that gateway of base station, there is some kind of backhaul connectivity to the internet. And the results of the sensor reading or graph or whatever they are will be visible to the user by means of a web browser. So this is the general case that applies to most IoT situations. One thing that is very important, we've mentioned that IoT communication is mostly by wireless, so you need to have access to spectrum. And of course, spectrum is a valuable resource, and the frequency allocation is country dependent. So every country has a different, and in particular, in the case of IoT, we have different administrations and different regions according to the ITU, and then each country also has particular requirements on the use of the spectrum. So I will not deal with the frequency allocation because this is strictly country dependent. And in each country, there will be some frequencies that are sold for action.
Excuse me, Emmanuel.
Yes.
Maybe the shared screen is a different content, I think. So could you check the screen?
Okay. What content are you looking at?
We see here LoRaWAN communication. That's maybe can you just show the slideshow? It's not on the slideshow right now. Maybe it's a different, but I have a different one and you're showing the different slide.
Okay, let me, I don't know what's going on. Okay. I'm sorry for the inconvenience.
Okay, there you go.
Okay, I switched to the PDF version because I was using PowerPoint, but apparently PowerPoint did not work well. Okay.
All right, yeah, we see now. Yeah.
Okay, let's start again.
Okay, so we're talking about the spectrum allocation. Can you see my screen now?
Yeah, we can see, but it's too big. Can you just?
Okay.
Yeah, it's
good.
okay now. It's okay. That's fine.
Okay, I'm sorry. Okay, so I'm saying that frequency allocation is country dependent. Cellular uses spends a lot of money in paying for the spectrum because the spectrum is protected. But there are also alternatives that use unlicensed spectrum, which has different requirements in different countries. But anyway, it's you don't have to pay normally for the use of this spectrum. And this opens up a lot of possibility, like the one that we all experience with Wi-Fi. Wi-Fi is possible because, I mean, the success of Wi-Fi is possible because of the availability of unlicensed spectrum. And these unlicensed bands are called ISM. And the big problem with those is that they are subject to interference. So you don't have exclusive right to use those frequencies. You have to share them with other users. And there are different methodologies to share the spectrum, but all of them are based on limiting the power. And then you have to take some other consideration in order to allow the sharing of the spectrum among different users. The most common one is listen before talk, like it's done in Wi-Fi. But this is not the best for IoT application. For IoT application, the one that is most used is duty cycle limitations, which can take the two different versions according to the regulation in the country. They can limit the amount of time that a given device is allowed to use the spectrum, or they can just set up a limit in the percentage of time that a device can use the spectrum. This is called the duty cycle. Also, there is the possibility of using certain frequencies that inherently do not travel very far without this constraint of duty cycle limitations. So in general, we see that this opens up the two possibilities with regard to low power wide area network communications. One is the cellular IoT, and the other is unlicensed spectrum. The traditional cellular communication is not well suited to the requirements of IoT. So the 3GPP, which is the standard body for cellular communication, devises two new technologies. One is called LTE-M for machine communications, and the other is called narrowband IoT. And both of these technologies are very well suited for IoT application, although there is still the problem that you have to pay a service, have to pay a significant amount of money for the service. So there are other vendors that take advantage of the unlicensed spectrum, and there are vendors like Sigfox and several vendors that leverage the LoRa technology. There is another company called Ingenu that also called RPM, and a new entrant in the field that I still have not tried, what is called narrowband fidelity. So these are the initiatives from the cellular vendors that offer different applications that are quite useful for this kind of application. Also in 5G, there is a standard called 5G New Radio Lite, which is well suited for IoT applications. So the vendors that offer non-cellular low power wide area network address the needs of consuming little power, and many applications do not have stringent latency requirements, and indeed they are able to offer high power budget, what is also called maximum coupling loss. This is the most important aspect for long distance and for a deep indoor penetration or penetration through vegetations and so on. So Sigfox is a company that offers this kind of technology, They have a wide market, but you depend on this single provider, and you depend on the fact that Sigfox has made a deployment in your country or your region of interest. Otherwise, you cannot use this kind of services. Here comes LoRa. LoRa is a type of modulation, which is a type of spread spectrum modulation, which takes advantage of the possibility of spreading the spectrum using a particular type of signal, which is called the chirp, which is a signal varying in frequency. This type of signals have been used for radar application for many years, but the advantage of applying it in IoT is that you can get you are able to detect this kind of signal with very low power. So even if the signal received is very weak, because of the gain you obtain by the spread spectrum technology, you are able to detect feeble signals. And this is what makes LoRa particularly attractive for IoT applications, because using a spectrum of, say, 125 kilohertz, you can send a very few bits per second, well, few depending on you will see how many in this next slide, but the idea is that you can trade throughput for distance. And this is by taking advantage of the channel capacity equation derived by Shannon in 1948, which states that the bandwidth, that the amount of bits per second that you can send is proportional to the bandwidth and to the logarithm of the signal-to-noise ratio. So for the certain amount of capacity, you can either use a bigger bandwidth or a bigger signal-to-noise ratio. So you can play with these two parameters in order to meet your requirements. LoRa is just a type of modulation, but in order to have a communication service, you need to have other protocols, and these protocols are offered by different organizations, but in particular, the one that has gotten more attention is called LoRaWAN, which is an ITU standard, which is controlled by the LoRa Alliance, and so many manufacturers are offering the devices with the LoRaWAN capabilities. So how is the architecture of the LoRaWAN in general? We have the same slide as shown before, but with a little more detail. Now we have an end device that communicates with the gateway, a LoRaWAN gateway, using of course, the LoRaWAN protocol. But from the gateway must be somehow connected to the internet by means of some IP communication of any kind. Can be a cellular service, can be a Wi-Fi long distance, can be a cabled Ethernet, whatever. The LoRaWAN gateway connects to a network server, which has all the intelligence in the network and has all the handling. The gateway is pretty dumb. The gateway only receives packets from the end device and forward them to the network server. The network server on its own will look at which application a given packet belongs to and directs to the corresponding application server. So the interesting idea of this architecture is that the end device communicates directly with the network server using a protected channel with the network session key. And the network server is not able to read the content of any packet, neither the LoRaWAN gateway, of course. Only the application server will be able to provide this information to the user, which is protected by the application session key. So there is an end-to-end encryption that allows for many users to share the same gateway and even the same network server, but differentiate because of the different application server. A big advantage of the LoRa communication is that it can use different spreading factor. The spreading factor is the number by which the bandwidth of the, or the throughput in this case of the signal is multiplied in order to spread the spectrum and make it easier to be decoded. So if we just multiply by 7, what is called the code gain of the system, then we can afford to have a signal to noise ratio of minus 7.5 dB. And this will afford a bit rate of about 5 kilobits per second. And the duration of each packet, a packet containing 10 bytes, will be 56 milliseconds. On the other hand, if we go to a spreading factor of 12, which means expanding the spectrum 12 times, in this case, we can make do with a signal to noise ratio of only 20 dB below the noise in the receiver. And this is quite important because it means that you will not be able to see this kind of signal in a spectrum analyzer because they is buried in the noise. But thanks to the spreading gain, you can decode a signal that is 100 times weaker than the noise. And this is what makes LoRa so special, because you can have a very low transmission power and yet reach very long distance. So by controlling this spreading factor, you can go for very long distance, but this means that the bit rate will be low, and also that you will be occupying the channel for a long time, 1.5 seconds in this case. Or you can go to if you are close to the gateway, then you can choose a spreading factor 7, which will allow you much faster bit rate and less time in the air. So these are the two, and of course you have all these possibilities in between. So this allows for a very long range. We have done some experiments here in Italy, in which if you have a clear line of sight, like the one I'm showing here between these two endpoints, then we were able to reach 316 kilometers with clear line of sight. And in the next presentation, Sebastian will show you that in the case of shooting to a satellite, the distance can be much, much longer. It can be thousands of kilometers. There is an interesting initiative called the Things Network that has been deployed worldwide by a crowdsourced initiative, and they provide gateways and the network server and application server free to use. And this is quite interesting because this has made possible to use the LoRaWAN technology in many places of the world, and it's still a good way to try the technology. You only need to buy a device and then know that costs less than $30. And then if you have a gateway nearby, you can start deploying the LoRa technology and deploying your own application for whatever purpose you have, and start getting involved with the technology. So this is a very useful initiative. We have been using this kind of network for a number of years in many countries, and it's very good to start using it. But for operational purposes, you are limited because the number of messages per day is quite small if you use the TTN, the Think Network. So other alternatives can be used, like ChirpStack. ChirpStack is a independent, open source and free to use implementation of the network server and the application server and the joint server that is needed in order to initiate the communication. And this, the advantage of ChirpStack is that it's free, you can deploy it, and using this technology, you can build your own network independently of any telecommunication operator. This is particularly useful for remote areas and for places in which there is no commercial service provider. Then you can build your own network just by buying the gateway, which nowadays you can buy for even less than $100. And you only need to buy your gateway and implement the chirp stack that can be implemented in a number of different platforms. And then you are good to go, and you are the owner of your own network. And the only thing you need is to have to pay for the communication between the gateway and the internet, which could be by means of a cellular service provider or by any other. If you are in an organization that has already Ethernet, cable Ethernet, you can deploy your gateway there, and the costs are included in the Ethernet service. Also, the advantage of the chirp stack is that the different network servers needed for the operation can be located in different places as long as they have IP connectivity between them, or can be just in a box. For instance, you can have a single box that works as a gateway, as a network server, and as an application server. And this is very convenient in some applications. Of course, there are also a lot of commercial LoRaWAN services, service providers that you can just leverage for service. If you don't want the trouble of running your own network, you can just buy the service from some of these. In particular, the Things Network has a commercial brand called the Things Industry that offer the service for free. For a fee, you don't need to worry about anything. You just pay the corresponding fee, and you can get all the advantages of the Things Network worldwide deployment. And these are some other providers. In particular, Helium is an interesting one because it has a different approach. Instead of paying with money, you have to pay with their own currency based on cryptocurrency they have on their own. So you can have the complete list of providers in this website here. Semtech, by the way, is the owner of the LoRa communication technology patent. Okay, here we have a comparison of some of the low power wide area network initiatives. We have narrowband IoT, which is from the cellular. We have LoRaWAN, which is the one we just described, Sigfox, and there is a new one that is called narrowband fidelity. This is a technology which I haven't had the opportunity to test yet. I tried to get, but I haven't been able to get. It's from Russia, and they, of course, claim to have all the advantages of the previous, because they are later in the market, so they need to offer different, they need to offer some kind of advantage. I haven't tried that, but in paper, they have all the requirement to provide a good IoT connectivity platform. But the interesting thing is that the bandwidth can be very different. For instance, Sigfox uses only 100 hertz of bandwidth to transmit 100 bits per second. On the other hand, LoRaWAN uses 125 to 250, in some countries even 500 kilohertz to deliver the same kind of service. So this is because of this Shannon equation, capacity equation that I showed earlier, that you can interchange the same bits per second. You can transmit with either using a very low bandwidth in terms of spectrum or a much higher bandwidth. But in this case, you are able to use a much lower power. So this is the kind of compromise that you can do by using the laws of physics. And the other thing you can see that the maximum payload is just about the same. We're talking about a few bytes. Normally, this communication will not support video, will not support audio, but they are very good for application in which you only need to have a few bytes in order to meet your requirements. An example of that is the meteorological data collection. And we have done that in many countries. And this is an example of an application in which we have a LoRaWAN gateway that is meant to receive data, meteorological data from a meteorological station. In this case, you can see that the meteorological station is outside the area of coverage of the cellular service provider. So the meteorological station could not use the internet service provider service because it's too far away or is blocked by some obstacle or whatever. So instead, we deployed a LoRaWAN gateway, which gets its connectivity to the internet by means of the cellular service. And this LoRaWAN gateway is able to transfer the data collected by the meteorological station to the cell tower, and from there to the internet, and make it available to whoever is interested in that information. But what happens if we want to have another sensor, in this case, an example of a LoRaWAN level meter sensor, and this sensor is outside the range of the LoRaWAN gateway. This is the range of the LoRaWAN gateway. I digress because normally the range is not a circle, it's just an idea, because it depends very much on the kind of terrain that is between the gateway and a given node. But suppose that in this case, this node is outside the range of the LoRaWAN gateway. In this case, we could try to deploy another gateway closer to that. But if we try to deploy a gateway in a place like this, which is outside the coverage of the cell tower, will not be able to work because the gateway needs to have cellular connectivity or any kind of IP connectivity. So to solve this situation, we developed what is called a range extender, a device that behaves like a gateway, but the only difference is that doesn't need IP connectivity. It only has connectivity from the sensor using the LoRaWAN protocol, and with the same protocol, it will connect to the LoRaWAN gateway, which does have internet connectivity, and from there to the internet. So this is the solution that we are working with, and yeah, so far has proved quite useful. So how do you implement this range extender? Well, we have tried different software platforms, and the first iteration used a Raspberry Pi, which is very well known, but is a little bulky. So we have another iteration that uses a concentrator called 1302 by Semtech, which is sold in this case by a company called SEED, that is probably very well known to anybody. And there is another version that is quite small and low power consumption, using just a Pi gate from the company called PiCom, which was recently acquired by another vendor because they went out of business, but now apparently they are still offering service. And you can see that here is a very small and very cheap and very low power consumption range extender that can be used to go beyond the normal distance that a LoRaWAN gateway can cover. So this is an example of the application that we tried here in Trieste. We have a gateway in a place near the seashore in the town of Trieste. And we had an end node at the distance of only 9 kilometers, but it could not communicate with the gateway because the line of sight between the end node and the gateway was heavily blocked by these obstacles shown here in the profile. So the direct communication was not possible. And so in order to reach the gateway, we deployed a range extender in a place that is just about, in this case, midway between the end node and the gateway, but is very close to the sea, so it's avoiding the hills that are in this region. And there is a clear line of sight between the end node and the range extender, and a clear line of sight between the range extender and the gateway. And that way made possible the communication using this small device that does not need internet connectivity, so it can be deployed just by using a battery, or even if you want to have a very long term, you can put a small solar panel and have it working for indeterminate time. Another example of the application of this range extender is by communicating from a cave. This is an interesting application because very often you need to have information sensor in a cave, like the level of CO2 or the temperature, humidity, level of water, whatever. In the region of Trieste, there are about 5,000 caves. So this is something that has been very much investigated, but normally communication from the cave is not feasible because the waves are attenuated by the rocks, and they will not penetrate very long in the cave. So we did an interesting experiment here in a big cave called Grotta Gigante in Trieste, very close from our lab. We set up the range extender inside the cave, but not very deep. And this position allowed the range extender to communicate with the gateway. In this case, the gateway was almost 10 kilometers away. Actually, it was in another country. It is in another country. It is in Slovenia, not in Italy. And by using this range extender, we were able to get the data from different sensors deployed inside the cave. So this is an example of an application that is, in this case, for the cave, but could also be extended to, say, a tunnel or even a basement in a building. Very often, despite the long-range capability of the normal LoRaWAN architecture, you might not be able to get signal from a deep indoor sensor like an electrical meter in the basement of a building. But if you set up a range extender in your house, for instance, then you can provide connectivity in this place that is not normally reachable. So this is one interesting application that could be used for many persons. This is an example, a real photograph of the cave we used for this particular application. And we were using this version of the range extender because there are many versions, as I showed you before. And the position of this range extender was exactly in here. And we had sensor in the floor, and we had, by the way, the floor is 100 meters below the opening of the ceiling. So this is, and the ceiling is at about 300 meter elevation. So this is about minus 200 meters above, 200 meters above sea level, and the ceiling is 300 meters above sea level. And so this is an example of the device that we deployed with a big battery and another device we use for logging purposes to see how was the communication inside the cave. Okay, so despite the problem with the with the screen sharing, I think we have covered some of the questions. And the conclusion we can draw is that IoT requires specific solution that normal cellular will not be able to provide. But with newer cellular protocol, they are useful for this kind of application, but you have to pay the service, and not always the service is available in remote areas. So the capability of doing your own deployment in a rural area, on an unserved area, is quite attractive. And you can do that either using some commercial LoRaWAN service provider, or you can use that by deploying your own a network and application server using a solution like ChirpTag. There are network available from different manufacturers, and we show that the effective LoRaWAN range can be increased using a range extender that we have deployed, we have designed and deployed on our own. So with that, I am open for questions if there is any.
Hermano, so the ARI, that works as a multicast, right? I mean to say that it's not a point-to-point.
Not really point-to-point, because it's always a sort of broadcasting, okay? So a gateway is able to receive from many end node server, even the one that not belong to the same organization, is a promiscuous gateway, because it can, any kind of traffic that is allowed, because you have to be allowed in the, you have to make a registration by means of what is called a joint server. But any legal user of the network can have their data transported by the gateway. No matter, you can have, you deploy your gateway, and your gateway will listen any legal packet will be transported to the network server. The network server will decide which application this packet belongs to, and will forward that message to the particular application. So you can have the same gateway serving different organizations, like one for meteorological data, another one for, I don't know, pollution, another one for temperature, humidity, another one for whatever you have in mind, even for alarm, okay? And the same goes for the range extender. The range extender is also promiscuous. It will receive any kind of packet, just like a normal gateway, and it will send them. But instead of sending them to the network server directly, it has to send them to any gateway present in the area. It doesn't have to be your gateway. It can be, in this case, for instance, in the example of the cave, we were using a gateway from stored in Slovenia. We don't even know who is the owner of that gateway. But because of the architecture, that gateway only received the message from our node inside the cave, and looked at the application. The application had a name, which in this case was called range extender. So it sent it to the network server, to the application server that had this particular capability, and we were able to look at our own data by means of the application server, in this case using TTN, the Sync network.
Okay, thank you.
Okay. Is there any questions?
Thank you, sir, for the wonderful presentation. To design a range extender, is it open source? Oh, my name is Abhimanyu Pandey, and a wonderful presentation. Thank you so much. Range extender, is it an open source, something we can do it in Nepal as a project in a school or a college?
Yes, indeed. We are still working on the details because we have different platforms, but of course it will be open source. It will be available to anybody to try it and use it.
Thank you. Thank you so much.
In NerdNet, we can also do range extender.
Yeah,
With a
kind
master
of.
design. Maybe you should
Yeah.
ask.
Okay. So previously I'm a Yasuno Wada from NICT, and we also interested in your presentations, and the LoRa we use the private LoRa, not LoRa one, so we can customize any kind of protocols, but you're using the LoRa one and also the extender. The extender is also based on the LoRa one standardized protocols, and to provide the relay. Is it correct?
Yes, indeed. This is the feature that we were addressing. The idea was to be able to use any deployed end node that is based on the LoRaWAN technology. And so you don't need to modify your end node. You don't need to modify your gateway, because the range extender is just a proxy for the gateway that collects the data from the end node, transmits it to the normal gateway, and from there on. So everything is LoRaWAN standard. The only thing that is different from the LoRaWAN standard is the range extender, the device that we built, because it uses the LoRa protocol to communicate with both the end node and the gateway. Okay, of course, as you say, LoRaWAN is not the only game in town. You can have other LoRa applications. There is a company called Links Lab, for instance, and there are many others that can deploy. Actually, the first deployment we did with LoRa was not LoRaWAN. It was a proprietary protocol that a PhD student was deploying when at our lab. And so we did some long distance experiment using that, which is LoRa, not LoRaWAN, because it was just for testing purposes. But we are aiming at LoRaWAN in particular because it is the most deployed, the most nowadays the most deployed technology. And so this is the idea, to leverage the sensors that are already inside, or the devices. For instance, we use commercial devices for meteorological applications, which use the LoRaWAN protocol. And we want to extend this range without having to modify either the end device or the gateway. Actually, okay, the LoRa Alliance is now addressing this field with a technology called repeater, that they already have approved, but it's still not yet available. And the difference with this is that in order to apply this protocol, you need to modify the end node and you need to modify the gateway. So it will be good for new installation, but it will not help in existing installations.
Okay, thank you very much. So the time is a little bit pushing, so we need to move to the next presenter. So thank you.